Now, for mechanical energy is the sum of potential energy and kinetic energy. So therefore, the formula typically is represented as mechanical energy is equal to Ke, which is kinetic energy, plus Pe, which is potential energy. Couple things we want to make sure you're aware of is energy is transferred from one form to another, and the total amount of energy is conserved. The reason why this little points here are important is because there's typically a relationship between potential energy and kinetic energy. I'm going to try to show those relationships in the following slides. So, in this example here, we have a ball that's not moving. Since it's not moving and since it's above the ground, it has potential energy, since it has potential to fall. On the flip side, if the ball is on the table, it's not moving, and since it's not moving, the kinetic energy that it has is zero. Okay. Now, if we happen to change a scenario where the soccer ball starts to roll off of the table, we have a different situation. In this instance, the distance between the ball from it to the ground has decreased, and since that has decreased, the amount of potential energy that the object has also decreased. On the flip side, because kinetic energy is increasing because it's in motion, it's obviously going to go up. So there's that relationship of typically when one is increasing, the other decreases, and vice versa. And now we're going to be showing the relationship of kinetic energy, potential energy, and mechanical energy using this simulation here. So just to give you guys a heads up, it's a simulation of a person skateboarding back and forth on this ramp. Right here, please pay attention to the bar graph. It'll visually show you the amount of kinetic energy and potential energy and the total, which is effectively the mechanical energy, on the left side of the screen there. So what's going to happen is that as I lift this individual, you'll notice that the higher and higher I place this individual, the greater the potential energy increases because it's higher off of the ground. So the higher it goes, the more potential it has to fall, the more potential energy it has. Once I press play, the skater will start to go into motion, and you'll notice that the potential energy decreases because it's getting closer to the ground, whereas the kinetic energy is going to be increasing because it's going to start moving. So as I press play, you'll notice that the kinetic energy is increasing, and once it gets to the very bottom of the ramp, that's typically when the skater is at its fastest speed, and therefore the object has the most kinetic energy and just a little bit of potential energy. And you'll notice if you add those two bar graphs together, you have the total energy, which is the mechanical energy. You'll notice that once again, the mechanical energy stays constant, the total energy is conserved. However, the amount of kinetic energy and potential energy you have changes depending on the location of the skater. Now, as we've also mentioned, mass is a fairly big factor in terms of energy. So right now, please pay careful attention to the total sign. You'll notice that as I decrease the mass of the individual, the total amount of energy decreases overall. So the maximum values of potential and kinetic energy have now decreased as a result. And since we're talking about energy, we also need to talk about ways where energy can be decreased. And so we're going to be talking about friction. Friction is effectively the resistance an object experiences when moving across a surface, or vice versa, which basically means the resistance a surface experiences because of an object. So some common examples of friction involve rubbing your hands together, especially when it's a cold day, or if a person happens to be sliding down a ramp, or if you happen to be just rolling down a marble down a ramp. And now we're going to be showing you the impact of friction and how friction affects the total amount of kinetic and potential energy the object has. So if you look at this graph here on the left, the thermal energy will effectively represent the amount of friction that is occurring in this example here. So once again, we're going to be lifting the skater up, and you'll notice that as we put her up a little bit higher, the amount of potential energy and the total energy is increased. However, if you put her at a lower spot, the amount of potential energy decreases because she is not as far off from the ground. So just built to show this, I'm going to put her at the very top as much as I can, and we're going to get this started. And you'll notice once again, as she goes to the very bottom, the amount of kinetic energy is increased because that's where it should be going at its fastest, whereas the amount of potential energy has gone down. Now you'll notice that thermal energy is going to be a factor here, so let's look at that carefully. One thing I want to note is you'll notice that I'll put my mouse here. As thermal energy increases, the kinetic and potential energy maximums seem to be decreasing as well. However, the total energy still stays the same. Now I'm going to pause it right about here. Perfect. Alright, so once again, if you add the kinetic energy with thermal energy, you'll get the total energy. So what's happening in this instance is that because of friction, the amount of kinetic energy is going down because it's effectively slowing the skater down a bit by bit every single time she does one iteration of going back and forth. So kinetic energy is going down, thermal energy is increasing in this example because the amount of heat being generated moving one place to another is going up.